Okay. Hi, I'm Hugo. This talk will be about introductory functional programming and games. So, me and all these other guys, we all come from the University of Minho in Portugal. And of course, these games are, or these snapshots are from games that our students actually developed. So we are gonna play these games later on in this talk, but first let me just set up some context. So at University of Minho, we are very strong advocates of a functional first school of programming, meaning that we have essentially been using Haskell in the very first programming course of our computer science degree. And we have been doing this for at least 20 years. So we really believe there are compelling and natural benefits to this functional first approach, but I hopefully don't need to be preaching to this choir. So the content of our course is pretty much what you would expect from an introductory programming course. You have basic data types, lists, sorting algorithms, trees, search algorithms, and so on. And this course also has a practical component and lab sessions, and at the end, the students have to do a practical lab assignment. And I was also a student at this university, and I remember that from when I was a student, my very first assignment was developing a command line stock management system. So I went digging into the records, and at least in 2005, that was still the case for our course. And we can say, sure, it works, it serves its pedagogical purpose of teaching the basic concepts, but it has a few problems. One is that it relies a lot on I/O. That is really not a focus of the course itself. And at the same time, it's not promoting the important parts of the course that are data structures and algorithms. And the worst problem or caveat is that this is not really motivating for students. And this actually becomes a problem because we still have unusually high dropout rates, especially in first-year computer science degrees. And on the left, you can find some numbers from our university showing that the number of students has been increasing. So we kind of owe it to ourselves to try to make teaching of introductory courses more appealing to a wider range of students, and at the same time, make our approach feasible for a large number of students. In our case, we have over 20 students per year. So this talk will be about our 5-year experience of restructuring an introductory functional programming lab assignment around a core idea of using interactive games. And at the same time, it will be about developing an automated assessment platform that can support our students and provide timely, rich feedback. None of these is actually new. So a lot of automated assessment platforms exist nowadays. And people from this community have been showing for some years now how cool games can be to teach functional programming from middle school to advanced courses. What we feel is unique in our setting is that we really have a very tight connection between assignment and the assessment platform, which means that each year we need to tailor this to each other. But hopefully we get more intuitive feedback for the students. And something also new is that we are asking our students to develop complete complex games from scratch and without assuming any prior programming experience. This talk is also about trying to reuse as many functional programming tools available to us to build our system. So moving on to an actual game. So this is a Soccer 1 game implemented by our students. We can use the mouse. We have different modes. Let's choose one. So this game is about pushing boxes, in this case, Pokemon balls into specific slots. Okay, there goes one. We can go back. Oops, I can change another player or another mode. I can change maps. So it looks very professional. It's pretty cool, very impressive for first-year students. let's try it another game. So we can use the mouse again, change the number of players, change the map size. So in this case, this is a bomberman game, so the objective is to kill off the other players by placing bombs. Okay, we get a power-up, we kill this guy, hopefully. So this one looks kind of retro, but you can see that there's a lot of work on it. So the transitions are very smooth, has a lot of sprites, and the logic itself is very well developed. Okay. So the main merit of these games is actually from Meyers' fantastic Glossy library that essentially breaks down writing an interactive game to 3 simple functions. Well, not necessarily simple, it depends on the game, but 3 main functions. One that reacts to keyboard and mouse events, one that reacts to the evolution of time, and one that renders our game state on screen as a picture. And this is very good for students because they don't need to deal with the usual technical details of developing a game. There's no I/O, no race conditions, and no complicated graphics. So they can really focus on the core components of the game. And you can also notice that the game state in these 3 functions can be any parameter S. So the first task of our assignment is actually to define a concrete game state for a specific game. And since we are targeting grid-based games, our map will just be a matrix. And a state will be a map plus some other information such as player positions, available items, and so on. And for the first task, we just ask our students to, given some description, build a game state. So to give you an intuition of the kind of feedback we provide, this is a live demo of the feedback page that we will be running for this semester's edition of the course. Apologies for it being in Portuguese, but hopefully you can get a notion of what's going on. So, okay, so let me just open this to speed things up. So students can define test cases on the left. And they can run their test cases against an oracle developed by us, these structures, and check whether their solution is functionally correct or not. So, for example, for this test case, they can see it visually as well to develop quick intuitions about the data types themselves. And if some case goes wrong, they can also check what went wrong by visualizing the results. So in this case, we can actually see that some pieces are not placed correctly. Okay, so moving on. So the second task of our assignment is actually to start developing the game's logic. And so again, we allow students to define tests. And they can, again, run their test against an oracle. In this case, a test is simply a state plus some possible play. In this case, we are rotating the player to the right. Okay, and in the second test, we actually start emphasizing to students the importance of defining good test cases. Otherwise, they may be testing their functionality without actually finding bugs. So at this point, we also provide additional feedback on the coverage of their tests. So this is probably too small, but you can see their second task is 88% coverage. And this is actually feedback generated by Haskell's HPC tool. So it also highlights the code that was run or not for the tests. Okay, so our third task is then an open task with no reference implementation, and it can be something as simple as asking students to define 2 functions to save and load game states to a string or to a file. And any solution such that loading a saved game state is equal to the identity function should be correct. And we have trivial candidates for this. such as the Haskell's built-in show and read functions. But for students to get a good grade, they actually need to develop more complex and incrementally harder to achieve compression strategies. So for this task, we simply rank student solutions to motivate them to compete against each other. Okay, the fourth task is then to complete the game's logic by adding timed events such as exploding bombs, as we've seen before. And for this task, we again allow users to define test cases and check their solutions against an oracle. But at this point, we also start emphasizing the importance of having a good programming style. And for that, we provide additional feedback to students about the quality of their documentation, pedantic compilation warnings, code refactoring suggestions, and so on. And these are all outputs produced by available Haskell tools. So, having defined a game logic, we can finally move on to animating games. And this boils down to writing the last function, a draw function that takes a game state and renders it as a picture on the screen. After doing that, students can easily combine all their functions from the previous tasks to build a complete playable game. The most challenging part here is if the students that want to add menus or other information, they will need to account for it by extending the game state and redo all the other functions accordingly. So the final task of our assignment is then to ask students to program some AI strategy that can automatically play the game. And our model for an AI is very simple. It's just a function that takes a state and produces some possible play, moving upwards, downwards, shooting a missile, something like that. You may notice that such an AI will have no memory. So when it does a play, it just looks at the state. For the next play, it has no idea of what it did before. So it's a very simple model, but it's challenging enough to have our students try out different strategies and see which ones work best or not. So for this task, for our feedback, we just organize tournaments in which we pair students against each other. So this is a race for bots programmed by our students. You can see some strategies that are more eager, some are more conservative. The mouse. Whether they are good or not depends on the map. So in this case, the eager guy will actually go through just by bouncing off walls. Kind of lucky, but with these different maps, students can get to try out different strategies, combine them, and so on. And I lost my mouse here. Okay. So over these 5 years, we have collected and bundled our assessment platform as a reusable Haskell library that other people can use and that we ourselves have used each year to generate grading and feedback reports. And you can check more details in the paper. Okay, some takeaway messages from this talk. So for instructors, yes, games are very appealing and effective to teach introductory functional programming courses. We also felt that as we improved the quality of our feedback, we were able to keep more and more students within the loop. And we also realized a not so obvious thing for us a few years ago is that we are actually able to push rich data types to a very early phase in our project. And with that, we are actually able to prevent students from falling into some bad programming habits that is usually about abusing strings and lists. And that kind of happened for some students in earlier phases of our experience. So by using that rich data types, we can cut it off. Some messages for developers. When building our system, Haskell testing and web frameworks were great. very robust. Haskell to JavaScript compilation using GSC.js is very robust, and we were even able to compile student code, as you've seen, without much effort. A not so good remark is that we have tried quite a few Haskell code analysis tools, and we feel that the feedback and the metrics are still sometimes hard to understand, and especially to convey to students. So there's still work that can be done on this. We also received very positive comments from the students. So in general, they just felt the course was challenging, but in the end, still very rewarding. For negative comments, you will need to check this paper. Okay, and that's it. So 2 minutes, okay. You can check out the games that I've shown you and many more in our Hall of Fame. You can check out our GitHub development, or you can try out the live demo for this year's edition of the course. That is still in trial mode. It's starting now in September, so if you find bugs, please let me know. So we still have some time, so I can show you another game. This one even comes with some animation. Okay. So this is a Micro Machines game in space, and I'm just being beaten by the student program AI, and I'm not really gonna get there. Okay, something cool that I can also show you. So we also include an Haskell debugger functionality now that we want students to use as early as possible. So this is a typical length implementation, and we can run the debugger. Wait a bit. And so get an idea of which functions were invoked. And we can also see an animation of the evaluation status of our program. So for the length function, we will unfold the input list bit by bit, and until we reach the empty list, and then we start traversing up. So free, and students can actually see that the elements of the list weren't actually necessary to evaluate this function. And I'm up, so that's it. Thank you.
So before we start with a question, there will be some closing announcements after those questions by Matthew. But I have a few questions. So a couple of them are related to that you're doing this in Haskell. So Simon Payton-Jones asks, much of what you described, good as it is, he would say that, would be equally applicable to building games in JavaScript or C++. How important is it that you are using Haskell, and why?
So Haskell was important because we are teaching functional programming, so that's a natural choice. For building the feedback page itself, we are just relying on a lot of Haskell tools, but similar tools which exist for other languages as well.
Right. So one tool, so John Hughes is asking about one tool that you apparently didn't use. You didn't use Quick Check for testing, and he wonders why not.
That's a premeditated choice. I didn't really go about that, but it's actually on purpose because automatic testing is very nice, but it really frees users from thinking about their code. So in this case, we are saying, okay, you need to write your own tests, and you need to think carefully about them. And we found that that helps in developing intuitions about the code itself.
Okay. So Jesper asks, how do you teach students to deal with the more complex type errors in Haskell?
We don't. So that's the problem. I know a few works about providing better compiler error messages, and that usually goes down to using simpler versions of Haskell without that many extensions. We haven't actually tried to do that. That's something that we could improve, so we just flash out raw escolar messages that can be very scary for students, but something to improve.
Yeah. So, well, there's a couple questions I'm just going to summarize that are related to how do you assess the effectiveness of what you're doing. I was also wondering that. You've been doing that for 20 years, doing the same thing. How does it compare with other approaches, more traditional?
So we didn't really undergo a serious study on that. We just believe it's better. Of course, we are biased, so, but yeah, that's something to be done in the future that we wanted to do, but not actually in this paper. So we would like to undergo a serious empirical study to assess whether it makes a difference or not. But in that case, we need to compare to other courses taught at the same university, and you can feel that may not be very pleasant for other people. So it's tough.
Yeah. Well, speaking from my own experience, I've often had some surprises from those evaluations. So there's a couple of questions related to how do you give students So Ken Shan asks, how do you give students feedback on programming style and design beyond testing? And is there any place for your automated assessment in that?
So for freshman students, it's often not easy to just promote good programming style. We do an intermediate approach, so we just give them the tools and the reports generated by a lot of tools and say, look, this is nice, you should look at it. And it works to some extent. So, for example, if we just show them code refactoring suggestions, it's very likely that they will try to follow them in some way and say, oh, I can fix this, sure. And little by little, we can improve their style. We feel it's better than just don't saying anything at all. But yeah, I think these tools could still be more tailored to first-year students.
Thank you very much. That concludes this session.
Thanks.